liquid level sensors for more than 25 years. So he knows what he's talking about by now. And with that, I'm going to turn things over to Bob. Bob, the floor is yours.
Thank you, Lee. Well, welcome, and thank you for participating in today's webinar. I hope you find this informational, and we look forward to your discussion and questions and applications to follow. Just to provide a brief history for those of you joining us last minute, Madison Company has been manufacturing float switches and reed switch-based technologies in the United States since 1959, so we're one of the pioneers. And as it's expanded over the years, we now include many different types of fluid sensors. So afterwards, feel free to visit our website at madisonco.com for additional information or contact us if you have any questions. There's several types and different types of sensors and sensor technologies for liquid levels, and there's many advantages or disadvantages for each. So what are the first considerations for selecting a sensor? Do you need a single point sensor for an alarm or to protect a pump? Or do you need a multi-point sensor to indicate different points to start and stop a critical process? Or do you need a highly accurate continuous level sensor to monitor processing fluids? So, is your fluid to be sensed under pressure, or is it in high temperature? If it is, typically we would recommend a stainless steel float switch or a sensor of stainless steel or durable materials. If you're selecting a sensor for high volume, low cost OEM, we can also do that. Or if you're looking for one-off custom tank switches, generally there are many selections out there to help you, or types to help you. So let's begin by reviewing each and considering these sensor types. Let's start with the most common, of course, is a basic float switch. As it implies by its name, these sensors float on the liquid directly to switch and indicate a level. Therefore, the first thing you got to consider with a float switch is the fluid type to be sensed and its specific gravity. For easy reference and convenience, the specific gravity of water is 1. So if you have a float that has a specific gravity of 0.5, that float body will float about halfway in the water and move properly with the fluid as shown above, or in this example slide. For best results, the specific gravity of the float should be at least 0.1 less than the specific gravity of fluid. This is so that there'll be enough buoyant force as it moves to overcome the liquid viscosity, and this will even work in thick materials like molasses, or it'll overcome the surface tension as it moves along a stem or the sidewalls of a tank, or if it's an optical sensor, that it'll clear off of the lens to help give good signal. So shown in this example here, we're looking at a tilt-type cable float switch. These are commonly seen in your sumps in your cellars or in tanks in your industries. Although they are typically larger than other sensors, their size allows them to carry a big electrical switch, larger than most sensors, and this can directly control large loads and pumps. Things up to half a horsepower or even 1 horsepower are not uncommon to be controlled by a tilt switch. They work well in tanks with turbulence and debris because of their size, which is often a problem for other sensors and sensor types. In this example shown also, the switch can change its state, or will change its state as it rises and falls around the weight, or the cable can be clamped to a pipe at that point to switch in a high and a low position. This is typically about 30 to 45 degrees above and below horizontal. The switch will change its state depending on the length of cable that you lay out from the weight or from the clamp to pump up or pump down the liquid. Typically this is about 6 to 36 inches of fluid change for most applications, and in a lot of sumps that's what you'll see. This switch is durable, but it's not really accurate, and its repeatability is not the best. But if you only need an inch or so of accuracy and just need it to go on and off durably and control that pump, these are ideal. The most widely used fluid sensors are magnetic float switch types because of their size, low cost. There's a wide variety of possibilities and design configurations that can be made up. Magnetic float switches need no additional power. They provide a direct control signal at the desired set point or at multiple points if you use multiple switches. These float switches provide a discrete, dry contact switch point, like turning on and off a wall switch in your home. It's on or it's off. It's pretty basic. Magnetic reed switch-based sensors like this can be made of plastics for low-cost, single-point commercial applications, or stainless steel, and this is working well for high-temperature, high-pressure, or sanitary food applications like fat food fryers up to 250 degrees C. So for special chemicals and low specific gravities like oils or solvents, we can combine metals and plastic floats to give a nice, durable, dependable switch that works well in the oils or other chemicals like this brass and Buna model you can see in the left of this slide. These magnetic float switches have been around for over 70 years because they're simple and they work, and that's why I got into this business. A hermetically sealed switch, it's in a glass tube with a nitrogen gas, is installed inside a sealed stem, and a magnet is sealed inside of a float that moves about the switch that's inside the stem. So when the magnet is positioned over the reed, there's a set of gold-plated contacts that are pulled together, and then they complete a circuit. So it's very simple dry contact, as mentioned. Most magnetic float switches allow the convenience to be set in the field to be normally open or normally closed by removing or flipping the float for a vertical float switch, or you can rotate the stem 180 degrees when mounting a horizontal switch. So you can see here in this slide, the example on the left is a normally closed vertical switch where the magnets are over that center gap of the reed in the center. On the right, you can see a horizontal switch that's mounted for normally open. The magnet is away from the switch. So that normally open, normally closed position is a question that we get often. For a magnetic switch, it's determined by the state of that switch at rest before the fluid acts on the float or changes the state of the switch. So in this example shown, once again, the normally closed vertical float switch and the horizontal switch is set for normally open. Most magnetic float switches have a small hysteresis, so that switch goes on and off in a very tight distance, typically 1/8 of an inch, but the repeatability is a 32nd around that switch point. This makes these simple switches a great choice for an accurate point-level sensing in most fluids or for fluid control. The contacts of these reed switches are typically only about 1/8 of an inch, or smaller even in some of the 10-watt and low-wattage switches that we sell and others do sell as well. So they can only carry a small amount of current. They have to dissipate that heat. So the ratings given for most switches are about 10 to 100 watts, and they're rated at resistive loads. And this is an electrical consideration that most people may or may not understand. But often these devices switch inductive loads, relays or pumps or valves, and controllers, which are inductive devices that create spikes during their startup or shutdown. These spikes are typically 5 to 10 times running steady state power given for most devices. So therefore, if you've got a 50-watt float switch, it should not be used for an inductive device with more than 10 to 12 watts rating. And for a standard pneumatic valve that may fit in the palm of your hand that's often used, these typically run about 8 to 10 watts and they're inductive. Or if you use a cube relay would typically run about 3 to 5 watts. So a 50-watt float switch would be good here. With proper circuit considerations and protection, like a varistor, which is another electrical device that helps clamp off these spikes, these float switches will work dependably for years and years to come, And we've seen switches that have been in service for 10 to 20 years come back, and they're always working well. And the customer bought that for only a few dollars. So what are some of these key considerations when selecting a float switch like this for a fluid application? If you have to select a cost-effective magnetic float switch for your application, consider your mounting configurations is really the first step to begin. And that may make it easy to select a simple stock product that you are looking for right away, or we can design a custom switch. Will you be mounting your sensor internally or externally, which inside or outside is the first question. So will you need a flange? Will you need an NPT thread? Or can you use a simple drilled through-hole device for a bulkhead mount, like shown in the first two switches here on the left? Each has advantages. The NPT and flange-type sensor mounts are commonly used for like high pressure, tanks, tank seals. We can do sanitary caps as well. The bulkhead allows for that simple drilled through hole for inventors and people who want to get a quick access into a tank. Often they're installed into caps of bottles for high level. But you can see that here in the different types of switches. In the middle we have a half-inch NPT, which also, that stainless steel model has a half-inch NPT on the back, which can provide a sealed thread for explosion-proof conduit and other J-boxes. If you have turbulence or debris in your application, these float switches can get affected. So a slosh shield can be used to stabilize or protect the switch from the chatter of the moving fluid or the debris that could damage the switch. The model in the lower right here, you see the stainless steel model, is an example of our 2-inch round high-pressure stainless steel float switch that you can see in the upper right here. And it's just got an installed slosh shield around it. Once you put this slosh shield on it, this device can be threaded onto a pipe, and then you can send it down into a bilge, or on top of a bilge is a high-level alarm. If it's on a long extension pipe, you can now put it down into agitating fluids or down into a well, and the slosh shield will protect it, but also it can hit the side walls of that deep well, and the float inside will still move freely. There's a set of small holes that are typically in the top cover and the bottom cover of that slosh shield, and that provides the internal switch with a smooth, level change, even though the water may be moving about quite vigorously outside. The most common failure for reed switch-based sensors like this is typically inrush, capacitive, or inductive load spikes, as I mentioned earlier. But if you visit Madison Co.'s site, we do have a reference center on there for electrical considerations and protection circuits. Or you can call an engineer or speak to our representatives. We'd be glad to help. But often these inrush currents may cause your device, that you're connecting to, or another device will be caused by the device you're connecting to or another device in line that you may not see. And this is a common occurrence and a call that we get often from a lot of customers using float switches. The most common encountered problem is this indirect current will tack the switch closed. To check this, often you can flick the switch with your fingernail or a tap of a screwdriver, and that vibration will free up the contact. It'll start working again. So people are often confused, why did this switch start working again once I uninstalled it and tested it on the bench? But if larger current spikes occur, they typically blow the switch completely open and they say, I powered it up and the switch is no longer working. But for an example, if you connected a 50-watt float switch to a relay to shut off a pump before a tank reaches empty, it's typically not a problem, since a relay only runs about 5 watts and then the float switch only sees a small inductive spike off of the 5 watts. So that's not a problem. But if you tap into a 110-volt line and you're connecting to a nearby half-horsepower controller for a pump, you may have a problem, because in this situation, the inductive pump is like a big electrical coil spring and will spike out down the ground line and blow out your float switch, even though it's only seeing that relay that pump is collapsing the field and sending a lot of electrical energy at many horsepower down the ground line, and on its way to ground, that power spike hits the float switch and it'll blow it open. So this is a common consideration. It's a grounding issue that a lot of people don't understand, but we do have some advice on our website to help with that, or they can call to talk to an engineer at any facility. You can also use these magnetic float switches, 2 or more, to set single points for pump control for signals by setting a high one and a low one to start and stop a pump, and then they're connected to a controller, or you can use a simple SPD relay to latch between the high and low switch for that pump control between 2 levels. So to save on installation, if you use multi-level float switches, this is a great advantage. On a single stem, we can put multi-point floats, and in this becomes cost-effective alternative, and it uses a multiple switch setup on a single intrusion into your tank. This option allows a great turnkey single intrusion into your tank or your application and avoids the cost and aggravation of building your own configuration from all these parts, putting them together. After selecting the correct materials to match your chemicals and environment, and selecting the proper mounting fitting, all that's left is to provide your switch designer with the distance from the mounting surface to each required level and the setting, whether it's normally open or normally closed. So that's, again, in the dry situation for the tank. Is it going to open or close when that tank is empty? And then you have to consider that for the operation during the pump up or pump down situation. Floats can also be selected for oil-water interface in single point or these multi-point sensors. And in the oil-water petroleum interface, since oils and petroleums have a specific gravity, we talked a little about that earlier, water is 1, oils and petroleums have specific gravities. They're usually about 0.7 or 0.8. So a designer would want to use a special float with a specific gravity of, say, 0.9, and this would sink through the oil, and then it settles and sits on the water interface underneath the oil. So this allows you to pump out water from underneath the oil safely, and then you can automatically stop the pump before the oils or chemicals are pumped out. And this helps many people avoid costly environmental issues, oil spills, and things like that. But you can also use this in applications where you want to do oil-water separation and clean out the fluids underneath the oils or capture the oils on top and transport them later and pump those off separately to a barrel for recycling or transportation elsewhere. At Madison, we can take the guesswork out. We can provide you with an expert to help you through this custom design process, and designers can go online to the configurator to build their own parts. We've built up our own configurator online that makes it easy and walks through these steps from mounting to levels to types in a step-by-step mode. Then it provides a direct price quote for ordering. This means that custom float switches and sensors can be made from your inquiry, and they're typically done in about 3 to 4 days in our process. So it's pretty quick for a custom part as well. Custom multi-level switches like these are available in many different materials to match even aggressive applications, including military-hardened and tested designs like helicopters. We put them in all kinds of marine use for the Navy. Multi-level float switches have been used in space flight and above the ocean surface on drilling platforms. And these are hazardous locations where if you need UL certifications or HAZLOC approvals for explosive device protection, these type float switches can do that because of the sealed fittings and NPT threads, which typically seal well in this. But also, these switches are often found in submarines hundreds of feet under the earth, or under the ocean surface, for critical functions, water monitoring, bilge, things like that. So they're found all over. Each float level switch is wired for individual indication, or it can be paired up, like I mentioned before, for pump up or pump down control signals. So with additional high-low level alarms, we can add other points if you want other functions. So typically a multi-level float switch can be made with up to 6 points in a switch, and it can be made up to about 20 foot long. But the disadvantage here is you're going to have quite tall, quite long device that's going to be costly to ship. For smaller applications like coffee makers, these multi-level float switches can also be made up in miniature plastic devices with 4 to 5 levels and manufactured in high volume to provide selectable cup filling dispensers, just like the coffee maker you may have in your office. And the cost for these is relatively low, typically under $10 in production volumes for OEM applications. Additionally, temperature sensors can be put in these for those coffee makers or other devices, or an RTD, and those can be incorporated into a hot water bath or a hydraulic or a pump system to avoid damage to the equipment by monitoring that critical temperature. So if you're in a hydraulic compressor, as that temperature gets hotter, it shows that your compressor has got problems. Or if that level gets critically low and your compressor is about to seize up, you want to stop that compressor ahead of time. So that's where a float switch or maybe a combination level sensor is ideal, to avoid just destroying thousands of dollars worth of equipment with a simple $10 to $50 device. Oh, thanks. Thank you, Ken. So these float switches, it's reed switch based. Since it's been around so long, it's also combined. A lot of people have put it into continuous float sensor setups. And like the slide that we've shown here, multiple reed switches are strung together and configured to create a step-style continuous level sensor. The reed switch-based continuous level sensor like this offers a cost-effective type sensor typically over other technologies, but its resolution is typically 1/4 inch to 1 inch between those step points of the resistance for resolution. And this is dependent on the distance between the internal switches as set by the designer, or for the application or the cost. A series of parallel resistors or reed switches like this, combined with a string of those resistors, are sealed inside the stem. So it's similar to the other float switches. You're protecting the electronics from the outside environment. But the output changes as that float moves up and down, changing the switches that are in contact during that float's movement or during that position. This resistive output can be used on its own, typically in fuel gauges and cars and other vehicles. That's a common application. But it can also be converted to a 0 to 5 volt DC output or a 4 to 20 milliamp output if you want to apply this to a digital readout. And these digital readouts, or a PLC, can be used, and you can get a numeric value that directly relates to either gallons or height or distance in the tank and the amount of fluid left. Another common application for these reed switch-based switches is for drums, 55-gallon drums and basic tanks. And we often have these sensors, or other manufacturers make similar sensors for 55-gallon drums in these common applications, ready to go off the shelf from top-level manufacturers like Madison Company. To aid in the automated processes and efficiencies of recycling, waste oil, liquid level recovery, or oil recovery, as we mentioned earlier, these systems utilize the custom sensor or the standard sensor here to call out before a barrel empties, or if it reaches high level, if it's filling up with waste oils. These sensors automate that fluid replenishment if you want to do that, or they can provide pickup notifications via hard wiring or cellular dial-outs to your local Jiffy Lube to come get those barrels once they're full of waste materials. And here we can see these 3 standard float switch types that we manufacture here. They fit the 3/4 inch bung, which is a standard fitting on most 55-gallon drums, but we can convert this through an adapter to a standard 2-inch NPT for home oil tanks and other devices. As shown, the PVC U3M ultrasonic continuous barrel level sensor on the right is an ultrasonic version that continuously monitors the level in a drum. This one's typically designed for 55-gallon drums, and it's programmable through push-button interface right to the barrel. So it's good for sensing that continuous level in the barrel, but it can also provide some alarm points. For single high-low level barrel systems, from that to ultrasonic level sensors like this UO3M, you can often protect against overfilling or costly spills or running out of key materials in an industrial process. Since we talked a little about that ultrasonic sensors, for high accurate continuous level sensing, we have ultrasonics as mentioned, and we have radar sensors. Both are designed around the theory of time of flight. It's a required time that the signal is transmitted, reflected from the surface of the fluid, and then it's received back at the sensor head. These continuous measurement sensors are accurate, typically to within a millimeter, or about 0.25% over full scale. Or that's the total height of your tank that you're setting it up for. One thing to consider would be the deadband of these sensors. This is the closest or minimum sensing distance that you can get to that sensor up towards the device. So what does this mean to a user? Full, if you put it at the top of a barrel, might stop reading at about 2 to 4 inches below the top of that sensor, below the top of that barrel as it approaches the sensor. So this can be eliminated if we simply add an extension tube to the top mounting surface of the barrel, extending that sensor just above to accommodate the deadband. The downfall with these devices is they're typically higher price, and that's what you pay for technology, but they're very dependable. So ultrasonic sensors, we got 2 here shown on the right, and they use sound waves, and it's receiving the distance from the sound traveling back and forth. Their ranges are typically a few inches to 50 feet with a nice 4 to 20 milliamp output. Ultrasonic sensors can be field programmable through push button settings right there on the unit, so you can set the full scale of your device right in the field, or you can communicate with like RS-232 or 485 to set the sensor distances before you get ready. The ultrasonics are nice because as they're vibrating to make the sound waves, they kind of keep their surface self-cleaned so they don't collect water droplets and things. But their downfall is that they're not good for carbon dioxide, methanes, foams and vapors, or even dust. And agitating fluids also can disrupt the signal so that you won't get a good sensor reading out of the ultrasonics typically. Radar, on the other hand, uses microwaves, so it can see through the vapors or foams and reach the liquid. They work well in gaseous liquids like carbon dioxide and methane, whereas the ultrasonics do not. These sensors are great for highly corrosive, acidic liquids and solvents. They can also be configured to read both the oil and water interface under ambient conditions. Since temperature can change the specific gravity of fluids, it's recommended that you know the temperature when using a radar to detect the oil-water interface. Microwave sensors like this can sense greater distances, so that's their advantage. And they can sense up to 100 feet or more. They're also field programmable, typically come with a 4 to 20 milliamp output or a 0 to 5 volt. But their deadband is typically determined by the length of their antenna. So you can see here that this one has a deadband of about 10 inches. The one on the left, that antenna that we have there, is about 10 inches. Optical sensors are another good choice for a lot of sensing applications needing smaller sensors. For applications requiring no moving parts, the optical sensor may be the proper choice. An optical sensor is designed for clean, non-coating fluids. These sensors can be mounted in applications as small as a 1-inch pipe via 1/4-inch NPT external pipe thread, or you can drill a through hole. If you can mount from the inside, you can use like a 1/2-inch through hole with a gasket and mount with a nut and a seal. But that emphasis again on that non-coating, a lot of people use these optical sensors, and if over time it builds up on the cone of the sensor, the infrared signal will not be read properly. So an optical sensor uses light, an infrared LED, which is sensed by a phototransistor inside that provides a switched output or a digital signal, digital output, or a small electrical load once the change of that reflection is sensed. They are intended to be mounted sideways, typically, or in the side of the tank, or in the bottom, as long as the liquid's shedding off the surface, or off that tip. If you mount them vertically from the top, typically water droplets can hang on that tip, and then you'll get a reading that there's water on your tip all the time when there's not. A lot of people ask us, how can I use this optical sensor if it's mounted adjacent to a surface, or if it's close by to another wall on the other side? Like, how small of a vessel can I mount this in? So to avoid false reflective readings with an optical sensor, it's typically recommended that you have a 1/2-inch or more of free space in front of the tip. For general purposes, that's a good rule of thumb. For medical or clean fluid applications, these plastic optical sensors are a popular choice. They're usually made of pure plastics that work well in medical and high-end chemicals. While industrial high-pressure applications, you can find sensors, optical sensors like this, that are stainless steel with a glass tip for higher pressure. Stainless steel optical sensors may be hundreds of dollars or more, while the plastic sensors can be sold for under $20. But these optical sensors typically will accurately measure the sensing at the tip within a 30-second. So they're very accurate point-level sensors. These are ideal for, like I said, small medical systems, fluid test stands, low-level hydraulic fluid protection. With built-in delay, these sensors are immune to splashing, so they're not just going to go off if liquid hits the tip. So this avoids chattering if there's splashing going on, and it provides a consistent reading when the actual level has occurred. But they've been used in high vibration equipment. Even in race cars, we've had people use these to sense oil levels in lower temperature hydraulic reservoirs for brake fluids and things like that. Another different type of sensing technology that's been around for many years is conductivity. Conductivity sensors detect the presence of liquid with no moving parts to run a pump or a controller, and moisture, or for leak detection, simple leak detection. Since this technology requires a conductive liquid, they won't work with oils or other non-conductive fluids. Conductivity sensors use a very small, low-power electrical signal to sense between the probe and the reference ground or the tank. When you contact the conductive liquid, the circuit is complete through the fluid. So that means the electricity is traveling through the fluid. But that is a very small amount of power, so it's very safe. These sensing circuits utilize a relay to provide that switched output, but are relatively still inexpensive. I mean, this is a pretty cost-effective device. But they do have a weakness. If proper considerations for the conditions are not considered, the electrical signal can cause chemical reactions known as electrolysis, and this will corrode the probes over time. And typically it's over years, but clean fluids aren't a problem. It's usually where you have deposits and things that can also scale up on these probes that the electrical circuit won't be completed and won't work properly. The Floodmaster line is a complete conductivity sensor system that allows for the use of the conductivity sensing technology and is used by plumbers all across the country to detect leaks, sound alarms, and then even shut off the water main for the smallest amount of water when it's detected in your homes or out in the industrial applications. This can cost people thousands of dollars, as you may know. By replacing the Floodmaster conductivity sensor with 2 float switches, you can also use this same system to control a pump up or pump down application, controlling the valve directly. Most conductivity systems like these provide output signals that can be hardwired to alarm systems or even provide a direct dial-up to send a message to a cell phone letting you know where the indication has occurred. It's an actual, some of these come with messaging systems that can transmit to your phone and say, hey, water heater at your home has just leaked. So it's a nice little system to have. For example, the field configurable probes on this picture shown at the top, this example on the top that I'm showing here, it's ideal for clean waters, and typically you just cut the longest probe for your common to reach the lowest point in your fluid tank or application. Then you cut off the other probes at the desired levels. The controller will sense between that common probe and then through that fluid to each point as it's sensed and touches the probes. So the applications that we've seen over the years are very common and very fun in a lot of situations. So float switches, radar, ultrasonic sensors are often used in dry docks to control and raise lower ships in repair. But how many times have you shot the water into the mouth of the clown at your local carnival? It's a float switch that determines the winner. Once the water inside a small tank that is captured by the clown's special mouth reaches the float switch, it actually fires a pneumatic valve, and that blows out and blasts the balloon and makes it pop. So sorry guys, if you're selecting that stretched balloon, it doesn't make a difference. Float switches, as we mentioned, can be used in oil-water separation, environmental, food applications. In food applications, one of the most common that we see is for fryers and high-temperature devices. So for food equipment, it's become one of the largest usages of our stainless steel float switch. So at your favorite fast food restaurant, these switches are often used to monitor and maintain that level so that there's a consistent level of oil, which guarantees that your fries or your southern fried chicken are always satisfying your craving. These high-temperature devices can reach about 250 C, as I mentioned before, so that's about 480 degrees F. They're also good in hot oils for hydraulics and other applications, hot glue dispensing, or chemical processing. And once again, remember, if we incorporate an RTD or a thermocouple or a switch into these devices, you can get both temperature and level sensing in one intrusion into your tank. Steam cookers and warmers are another good cost-effective use of a liquid level sensor, float switch, or optical, depending on the temperature. In your home, you have humidifiers and coffee makers, as we've mentioned, are key equipment that are used in using these types of sensors. Typically, plastics are good for boiling waters and below. Stainless steels on a standard float switch or optical sensor or other types are limited by the electronics. Float switches can go higher to 150, whereas optical sensors are typically limited to around 100 degrees C, which is about 200 degrees F. So where might you imagine your next fluid sensor application? Do you want to design a new coffee maker? How about putting one in the windshield washer fluid bottle of your Hummer so that if it gets low, you won't have to run out. You can see that it's already detected it. Since many of these small sensors require little or no power to activate or switch for a switch to close, they're often used in remote locations to trigger refill valves, small systems and those can be connected to a battery. You know, a lot of times we get farmers that call us and they create their own livestock watering trough out in a remote location using a level sensor like these we've all discussed, the point level sensors typically, and then they combine it with a battery, and they just need a little bit of guidance, or they go out on the internet to find out how to do it themselves. So, in conclusion, whether you need a single level sensor or a sensor system for a high volume OEM application, there is a proper sensor to meet your environmental needs, your cost sensitive or unique application requirements. They're already in use all around you every day. So just imagine where your next fluid sensor can be used or where we can design one for you. Then call us here at Madison Company, and we'd be happy to put together a fluid sensing device for you and use our experience, our many years of experience here, and get you going. So I think it's to question time, Lee. Is that correct?
Sure is. Okay, thanks for that, Bob. A few of you have already submitted questions, so we're going to jump right in. If you'd like to submit a question, type your question into the question window on the side of your screen and then hit the submit button. While we're answering your questions, we'd also like you to complete the feedback form, which you'll find located through the red survey icon in the toolbar below the slides. And with that, let's get into our questions. The first one here, one of our listeners wants to know the highest temperature you can have for a float sensor.
In the reed switch-based float switches, which have the greatest temperature range, we've gone up to about 300 C, but the problem typically at the higher temperatures is finding wires that are electrically rated or UL rated to meet super high temperatures. So there are some limitations. The switch itself can handle these conditions to 300 C, but typically we say 250 C is our standard high temperature. And just for note, we have used these in cryogenics, and they've worked in applications to minus 40 C. So people have put them in some pretty tough applications for us, temperature-wise.
Okay. Any temperature limits on those ultrasonic or radar sensors?
Yeah, once again, as I mentioned, the ultrasonics and radars are typically limited by the electronic circuitry, and electronic circuitry are usually limited to about 125 C, or in some cases even lower. Or in Fahrenheit, we're usually around 180 or 190 degrees Fahrenheit because the plastic electronics, the electronics have to dissipate some heat. So if that helps answer that question.
Okay, that kind of gets us to our next one here. Another listener wants to know if an ultrasonic sensor would work in a continuous water level for any type of container. In other words, plastics, or does it matter if it's a plastic, a ceramic, concrete, or what?
No, it typically doesn't matter. The ultrasonic sensors can see down and reflect off the surface. And actually, we work with and develop some ultrasonic devices that look up through the surface or through the bottom of the tank, and they'll reflect off that surface change as well and reflect back to the bottom of the tank. So ultrasonics can see through even the tank as long as we couple to it, but they're looking for that oil-water interface, which is where two, let's say, specific gravities, which air is near 0 and water is 1. We're looking for that to reflect the sound waves.
Okay. Another listener would like a recommendation for the best kind of sensor to use in a wastewater tank.
If it's large debris waste, that tilt switch that we, I think we can even go back on the slides if we want to. We'll try to accommodate that real quick here. But, so I think it shows up now. I'm not sure if that goes live, but the tilt type switch is large and that can overcome debris. But Float switches, the large 2-inch stainless steel size multi-levels can also work well with debris and can be installed in that slosh shield, like we said. And the slosh shield can be even a large tube that they create themselves with a hole at the top and the bottom, so the fluid runs in and out, and the float moves with the fluid while the debris is kept away from it.
Gotcha. Okay, next up, we have a listener who'd like to know what's the maximum length you can build into a multi-point float. We talking feet, yards, furlongs, what?
Yeah, we mentioned it's on one of the slides, but typically we can go up to 20 feet. But the downfall is that it becomes this half-inch or three-quarter-inch piece of pipe, just like you handle at Home Depot, becomes a little whippy, and then you have to kind of have that same amount of free space above the tank to try and drop it in, or below if you're sliding it in from the bottom. But typical applications range 8 to 10 feet for us, or for most float switch manufacturers.
Okie dokie. Are there any float switches that are Class 1 Div 1 rated?
Yes. There are many out there. Many of our competitors do not have these certifications, but we do. We have FM, we have Class 1 Div 1, and it's not just on float switches. Some radar and ultrasonic devices do have these ratings, but it's typically something that we have to go out and get approvals for, and we have already done on most standard multi-level float switches. Yeah, so I guess that answers the question.
Stainless steel.
Okay.
Yeah, typically that's in stainless steel, too.
Gotcha. Okay. Now the listener would like a recommendation for the best kind of sensor you might use for sensing water in a tank like you might find located on a roof of a house or maybe buried in a yard somewhere.
Okay.
In other words, pretty remote, I think, is what he's getting at.
Oh yeah, if you go onto the New York City skyline and you look, a lot of those buildings still have those old water tanks up top, and those are usually used for fire protection, and they're old wooden barrel type, but it's amazing to see. But it's common to use the tilt type float switch, or even stainless steel single point switches cast down or attached to an extension pipe so that they can be sent down to a correct level to give a low location, or a 2-level switch is used typically to give a pump on, pump off, in a ground tank for a cistern. If you want to use that for watering a garden or hydroponics, you capture the water and the 2 floats can be used to go on and off for the pump. But tilt switches are the most common because of their one cost, $65, direct control right to the pump, can control a half horsepower to 1 horsepower, whereas a float switch, you're going to need to connect that to a relay to handle anything larger than, about 1/8 of a horsepower.
Okay. Another listener would like to know if you can give them some guidelines for choosing between contact and non-contact sensors.
I think typically for contact and non-contact, in non-contact, a lot of times those are continuous or there's more electronics involved. Like I said, you get a 4 to 20 milliamp with a continuous ultrasonic sensor. So, I think cost is the point that you have to consider. Or is it a high purity application where you can't touch the fluid? Then we can use ultrasonics to see through the fluid. So there's an application where ultrasonics, not discussed here, but if it's a medical application and you want to see inside of a small medical vessel or a tube, you can detect when a bubble or a gap of the liquid is inside that tube or vessel. So this is becoming common now for medical devices to use ultrasonics as a non-contact by seeing through the tube, but in an application where it's just water or something that doesn't matter if you're in or out. I think cost becomes, or the mounting type becomes the bigger choice for why would you select a certain application part or sensor.
Okay. Got another listener who would like to know about selecting float material, and basically what he wants to know is, how do you select the float material if you know, for reasons other than just the cost of the thing?
The specific gravity is key, and that's where if the slide for single point sensors is up on their screen, or if they want to print it out later, in the upper left there's a very small miniature float switch that we sell, which becomes common. Everybody wants a little bit smaller device, but being that that device is small, the buoyancy of the float is only about 0.9, so it'll float in water. And often people take those type switches and say, hey, I want this float, and then they put it in an application for gasoline, and it won't float in gas because gas is at 0.7 and the float is at 0.9, so the float sinks. So selecting the float, there's a lot of guidelines that are on our website. We have a good resource center there, or our people can help. But typically you have to set the float to match, or the device to match your specific gravity.
Okay. Right? Another listener wants to know if you can use an optical sensor in liquids that are kind of milky, kind of like machining fluid, whereas we also got debris floating around, like metal particles.
Yes. Typically, they'll work fine in those applications. It doesn't matter whether the liquid is clear or opaque. The sensor tip acts like a mirror, whether that fluid is clean, dirty, or otherwise, solid. But the only consideration is that will it coat the actual optics? And it may take a while, but if a little bit gets on the surface, it'll be fine. But over time, as it builds up a big film, that will affect the sensor's reading. So it can be clean, typically, with basic rubbing alcohols, or even a clean basic rag or soap water material. And so if it's a system that gets slightly dirty, a preventative maintenance cycle or cleaning cycle once a month, once a week, once a year may be needed. But the milky material or debris typically shouldn't have a problem with an optical sensor as long as it's shedding from the optical tip.
Gotcha. Another question here is about float switches. He wants to know, how do you tell if a float switch is set for normally open or normally closed?
Yeah, we get a lot of people that call, put the switch in, and they say, I've got it set normally, it's closed all the time, what should I do? A basic ohm meter or continuity tester is the best way to check. By having the leads free from the float switch, you can connect to it with an ohm meter or continuity tester and see if it gives you a short circuit or an open circuit. And then once again, if you want to change the float, if it's a vertical float switch, you can remove the clip, flip the float over, and put it back onto the stem, and it will change state. Or for a horizontal switch, you would rotate it 180 degrees while it's being mounted, and the switch will change state. Excuse me.
Sometimes it's marked, too. Sometimes it's marked.
Yeah, and often on a lot of our switches, there's a mark that may say NO or NC, and actually on the slide for single-point float switches, on the upper right, that round ball has an NC or NO to indicate which way is it set.
Okay. Here's one about optical sensors. The listener wants to know whether an optical sensor will sense a foaming condition, and if so, what's it going to do? How's it going to react?
Typically, an optical sensor won't see the full foam. It has to have enough liquid on the tip that it will reflect or refract the signal into the photo transistor. So if foam starts to hit it, it depends. It's an application-specific thing that you'll have to check. But typically, basic foams like soap foam won't affect it. It'll wait for the full liquid to hit the tip.
Okay. Another float sensor question. Can you use these things in conditions where there's constant shock and vibrating? And he specifically mentions flight vehicles.
Yes. We've used these in aerospace flight, and helicopters, and to do that, they typically test the devices on a shake and bake table for military testing at high and low temperatures while under severe vibration. So typically they work well. We use them in road eaters. We've put them in applications for the machines that go and chew up the pavement before they resurface. And the vibrations there are very aggressive. But if the proper clips or retaining mounting and other connections are made on the float switch, they handle those vibrations without any problem. Very durable switches lasting over time.
Okay. Another listener wants to know if it's possible to make multi-point sensors in a modular way. In other words, so they can be adjustable.
Yes, we actually sell a kit that you can purchase directly from stock here that can have 2 to 4 floats, and they would cut the lengths for the positions that they want, and they put them together with compression fittings so that each float is held and sealed inside the pipe. So these work well for one-off test applications, but over time, once the device is set in the field and they feel comfortable with it, we can make a multi-level to mirror that. Also, they can be made with a compression fitting at the top of the stem, and that way they can slide the stem assembly up and down to change the levels that they're controlling right in the field.
Okay. This foam application seems to be kind of a hot topic here. We've got it for optical sensors. We've got another question on that. What he wants to know is, can you tweak the gain on the sensor so it does indicate that it sees something wet when there's foam? Or is it some kind of a custom part you have to do?
If it's a larger tank, that's where the microwave typically can be set or tweaked for that. I think I would have to defer that to a little bit of testing and design. Ultrasonics may work well there. There are gap sensors and things we could design, and if it's a specific fluid, we may be able to tweak the frequencies so that it sees that, but typically the air is going to affect it in that manner. So I think we'd have to, I don't have a clear answer on that yet. It's not something we typically do, but I think it could be done.
Okay. And I think we've got time for maybe one more. He wants to know how you determine, when you're talking about, he's talking about a mercury float switch, and wants to know how do you determine the position from the bottom of the tank? Or how far away from you are from the bottom of the tank?
Yeah, if it's a mercury float switch, those are typically those cable and ball tilt type. We don't typically sell those because of the environmental issues, but they're set for single point. So they don't measure continuous to let you know how close you can get to the bottom. Being that they're about 2 to 3 inches in diameter, those mercury switches typically will only go off or on about 2 to 3 inches above the bottom. You won't know how close you are. You'll just know the set point that switch is closed or changed state.
Okay. And with that, we're kind of out of time. Bob, we've got a few more left. Can you maybe answer these by email?
Sure. We can have someone send them in to us. We'd be glad to work with them, and
all right.
That's our job.
Okay. I think we've got their contact information, so we should be set on that score. But with that kind of concludes today's presentation. So for everybody, I'd like to say on behalf of Machine Design, I'd like to thank you for joining the webcast, and thanks to Madison Company for sponsoring this event. And I hope you all have a productive remainder of the day. Bye-bye now.
Thank you.